Welcome to our Exam 3 review for Organic Chemistry 1. In particular, this is going to focus on Gilchrist's upcoming exam that is going to be over mechanisms and nucleophiles and SN1, SN2, and all that kind of jazz. So, you ready to get into this?
Yes.
All right. So, we may not have time to go over every single question in the review, but we can at least cover most of them. So, do you want me to just go ahead and dive into the test? Do you want us to go ahead and skip number 1? What do you think?
I think we can skip number 1.
Okay.
That's fine.
So, question number 2 is actually surprisingly difficult. A little bit more difficult than you might expect. Question number 2 is about the ranking of nucleophiles. Okay, so there is a couple of different factors to consider when you're talking about nucleophilicity. So essentially, for something to be a nucleophile, it has to have the ability to donate electrons. So in other words, it has to have a lone pair of electrons that it is willing to donate. It needs a lone pair of electrons. Okay. But in addition to this, I'm actually going to go ahead and zoom in a little bit. In addition to this, you also have the issue of polarizability and basicity. So in general, after having a lone pair of electrons, the next most important feature of a nucleophile is that it is polarizable. And generally speaking, that means bigger atoms. Bigger atoms and more electrons are going to be more polarizable. And then lastly, we want to consider basicity. Basicity. Because the more basic something is, all other things being equal, usually, well, I misspelled usually, that's pretty sad. Usually means more nucleophilic. Okay. So when you're looking at these, at each one of these, the atom that is the nucleophilic atom is going to be oxygen in every case. So each of those oxygen atoms has approximately the same nucleophilicity, or rather, approximately the same polarizability. Okay. If you compared oxygen with sulfur is obviously much bigger, so therefore it is more polarizable. Note, like I mentioned here, that the first and most important thing is it needs a lone pair of electrons. It cannot be a nucleophile without one. The second most important thing is polarizable. That's going to have the second biggest effect. And then the third is basicity. All right, if you look, now, obviously things that are more negatively charged are going to have a tendency to be better nucleophiles. The more negative it is, the better a nucleophile it tends to be. And that kind of goes along with basicity as well. Obviously, things that are more negative, all other things being equal, of course, are going to also be stronger bases. So in this case, the best nucleophile, since they all have similar polarizability, the best nucleophile and the worst nucleophile can be determined by basicity. Which of these ions is the most basic? What do you think? I see one of you unmuted, but I'm not hearing anything you're saying.
Maybe the CH3O minus.
Yes. This is the strongest nucleophile, the CH3O-. Deprotonated alcohols are actually stronger bases than hydroxide. So CH3O-. So that is going to be stronger. And what's the next strongest nucleophile?
OH minus.
OH minus. And then the next strongest nucleophile is going to be the CH3OH, of course. So all of them have oxygen, all of them have a lone pair that they can donate. But if oxygen has a negative charge on it, it has an extra lone pair to donate, and it can donate without having a positive formal charge after it donates. So the most basic in this case is CH3O. That's going to be the best nucleophile. Now, there is some debate as to whether or not, I mean, like one could say, like, well, isn't methanol or methoxide more sterically hindered than hydroxide? And the answer to that is yes, but not appreciably so, not significantly so. And in truth, I mean, it depends on, I mean, different professors might have a different take on this, but that doesn't necessarily affect its nucleophilicity so much as it affects its ability to get in there as a nucleophile. So like, for example, tert butoxide is incredibly sterically hindered. It's a big bulky base, but it's still a good nucleophile if you have a non-sterically hindered substrate. Like in the case of if you have a prime, well, if you have a methyl substrate or something, or like methyl bromide or something like that. But there are some professors that would say no, because it's sterically hindered, it's not as good a nucleophile. We would not call that a strong nucleophile. But it's more like it's a strong nucleophile that's prevented from being able to do its job as a nucleophile. Does that make sense?
Yeah.
Yeah, there's the difference between having the ability to be a nucleophile and being able to carry out that ability. And steric hindrance affects the ability to, or affects carrying out that ability. It doesn't necessarily affect the ability per se. At least that's what I would say. But what do I know? All right. Number 3, it says draw the structure for the transition state of the following substitution reaction, and then draw the product for the reaction, and where D is deuterium. In this case, you're dealing with a chiral carbon, and you're looking for essentially the stereochemical configuration before and after. Transition state, typically what you want to do is you want to turn the molecule such that the leaving group, which is in this case the bromine, is facing to the right. And then from there, it doesn't really matter what you do with the others, except that you should recognize that if the leaving group, and actually let me erase that, I'm going to move that over a little bit. If the leaving group is to the right, you want to give it a little bit of space, because in the transition state, this is going to be in the process of leaving. The leaving group will be in the process of leaving. Who knew? And then the other part, the other 3 atoms that are connected to this originally are going to be in kind of sort of trigonal planar formation. So it's going to look kind of trigonal planar-ish. And you can have 2 groups up, and you can have 2 groups down. It really kind of is up to you. But in this case, I'm going to say 2 groups up, because if I rotate this around such that the bromine is out in the front there, that would put the deuterium up here and the hydrogen here and the CH3 down here. Now the oxygen is the one donating its electrons, so I'm actually going to put that here. I'm actually going to show the lone pairs of electrons that oxygen is donating as a dashed line. It's going to be dash, 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 dash. And it's in the process of donating those electrons. Whereas bromine, I'll show its lone pairs, but I'm also going to show its lone pair that it's taking with it, that it's leaving and taking with it as a dashed line as well. So in this case, you would also show a partial negative on the nucleophile because oxygen is in the process of donating its electrons. So it's not going to be a full negative anymore. It's starting to connect with the carbon. And bromine's in the process of taking those electrons away. So it's going to be a partial negative as well. So you can pull that over there. And so this would be your transition state. Does that make sense?
Yeah.
This is in the process of leaving, and this is in the process of coming in. And really interesting, the reason why you get this inversion of configuration with the backside attack, it's kind of like, has anybody ever seen the movie Mary Poppins? Like the classic one? I know this is an odd thing to bring up, but.
Yes, but I'm not sure where it's going.
There's a part in the movie of Mary Poppins where the umbrellas of everybody, because of those strong winds, starts flipping over. And there's actually several different things, like also when Mr. Banks gets fired, they like flip his umbrella over to the other side. Like they put it all the way up and then like pops out the other way so that the umbrella goes from being like to being like this. Okay, that's effectively what happens. The molecule starts out kind of like facing this way, and then it gets popped over to the other side. The three groups flip over because of the leaving group. The leaving group leaves and a new group comes in, and you get popped out to the other side. And that causes an inversion of the configuration. I don't know if that little explanation helped at all, but hopefully it gave a little idea of what's going on there. All right, so let's take a look at the next one. It says, write the mechanism and predict the product, including
Sorry,
scenario.
really quick. On number
Yep.
3, we're supposed to draw the product for the reaction also.
Oh, okay. Yeah. So in that case, if we were to finish this out to draw the product of the reaction, we could just complete the umbrella flip, basically. That's actually a good idea because now you get the other end of the umbrella flip. The hydrogen's been flipped over to the other side. The deuterium flipped over to the other side. The CH3 is now pointing to the other side. And then on this side, you have the OH that's connected to it. So that would be your product. So if when you turn this around, the original look of this particular molecule is you have the deuterium out this way, and you have, so the hydrogen is in the back, the deuterium is in the front, and you have the bromine here, and you have the CH3 here. And then it gets flipped over, it pops over, everything pops over to the other side when the OH comes in. So this does this, OH comes in, flips everything over to the other side, and now you have your product. Did that make sense?
Yeah.
Cool. All right. Any other questions on that? The transition state can mess with your mind a little bit, but if you keep in mind, like, I think it's the easiest thing to do is just to reorientate the molecule so that the leaving group is facing to the right, and then you can just set it up like that, the transition state. All right. Now let's take a look at the problem number 4. It says, write the mechanism and predict the product/products, including stereochemistry, for the following reaction. It said acetate is not a strong base, but it is a good nucleophile. Okay, so she's expecting you to be able to distinguish between when you're going to have SN2, SN1, E1, and E2. Okay, I actually came up with a rap to remember all the all the different things. Yeah, it's a parody of Baby Got Back, and it's yeah, it's pretty funny. But I may or may not. What'd you say?
So can we please hear
It's like, I
Share
like
it.
big. It's like, I like big bases and I cannot lie. Y'all other chemists can't deny. When a big bulky base gets in your face, elimination makes the H get sprung, and then you'll see C double bond to C. Steric hindrance is the key for the E2 mech2 base. So, I actually go through a lot more. I'll actually share it with you. I mean, I'll actually send it out in an email to you.
Please.
Thank you.
It's kind of ridiculous. There's somebody who there's people who do a lot better job of actually like the rapping part, but the rhyme that it came up with is pretty ingenious, I think. So maybe we'll have to make a music video. All right. But in this case, so you got actually, let me pull something up for you because I think this is going to be really, really helpful. It's my elimination versus substitution flowchart. So let's take a look at this. tccd.edu. Bam! Okay, academics, academic help, labs and tutoring, virtual learning commons and Canvas, and science support. I know it's awful, there's like 15 clicks to get here, but not quite that bad, but all right. So under concept reviews on the Organic Chemistry 1 science support page, there is the substitution versus elimination flowchart. And this is awesome, 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 awesome. When you actually see it, it will be awesome. Oh, there we go. So it has a list of your strong nucleophiles, your good nucleophiles, your moderate nucleophiles, and your weak nucleophiles. It also has a list of strong bases that are good nucleophiles and strong bases that are poor nucleophiles. And then you will have your good leaving groups. So now, if we look at this, generally speaking, if you have a primary carbon, and maybe I should have used some other color than yellow, but primary carbon, if you have a nucleophile that's not a base, you're really just getting SN2. Okay. If you have a nucleophile that is a strong base, you're still probably going to get SN2 unless the base is not a good nucleophile, or if the base is very sterically hindered, then you might get elimination. So going by this particular practice problem we have here, it says, write the mechanism, predict the products. Okay, so what type of leaving group do we have here? Is it primary, secondary, or tertiary? Is that a primary, secondary, or tertiary carbon that has the leaving group on it?
For the secondary?
It is secondary. Very good. So that carbon is actually connected to two other carbons, and therefore it would be considered secondary. And so because it's secondary, secondary unfortunately is the most tricky of the three, primary, secondary, and tertiary. Because secondary, you can really get both. So the question is there a strong base present? That's the first question you should ask. And the answer here is no. It actually tells you in the problem, this is not a strong base, but it is a good nucleophile. So that answers these two questions. These should always be the first two questions you ask yourself. Is there a strong base present? And is there a good nucleophile? In this case, there's not a strong base, but there is a good nucleophile. So you have a secondary carbocation, not a strong base, but it is a good nucleophile. We are going to have SN2 only. So then we can go back to here and recognize, okay, so this is going to be SN2. So this is going to come in and it's going to hit this with a backside attack. And because it hits it with the backside attack, it's going to flip the configuration. It's going to actually come in okay. And we'll switch colors. We'll do this one. It's going to come in from underneath, and that's going to pop the hydrogen up, but it's also going to pop the bromine out. And so when that happens, you're going to get the hydrogen is now in the wedge position. Although admittedly, you would not actually have to draw the hydrogen. But the dash position is going to be this acetate molecule that has come and attached here. So in this case, there is only one product that you get. Now, it is notable that this has, this is a wedge and this is still present. So this is going to be the specific product that you get. Now, like I said, you wouldn't have to show the H. You could actually get rid of this if you wanted to. And you could just do that. But you could also show the H if you wanted to as well. It's up to you. But this is a simple, straightforward, concerted step mechanism. It all happens at once. The oxygen comes in, donates electrons, kicks the bromine out, and you got your product. Any questions? Okay, I'll skip to the next one. Let's choose an alkyl halide and a nucleophile that could react to produce the following compound. So this is a really interesting problem because theoretically you really could get more than one answer here. Now, chances are if you're going to put this together, the only atom here that could have been nucleophilic is likely this oxygen. Because remember, a nucleophile has to have a lone pair of electrons, right? And there's none of these other things. Carbon doesn't really tend to have lone pairs of electrons, right? So none of these other things really could have been your nucleophile. It would have to have been the oxygen. So either the oxygen somehow attacked this carbon and formed a bond with it, or the oxygen somehow attacked this carbon and formed a bond with it. Now, there's a couple of different possibilities here. I'll go ahead and erase my little arrows and I'll look at like where I could have potentially cleaved this. So I could have cleaved it here, or I could have cleaved it here. Now let's take a look at one thing at a time. So let's say we cleaved it here. So let's say if we had this, there's a couple of different possibilities. We could say I have this butoxide, or rather terbutanol. I know it has to have the oxygen. So this could either be terbutoxide, a negatively charged one, or it could be terbutanol. That's a possibility too. And this would be your nucleophile. Well, so either one of these theoretically could be your nucleophile. Now, the other group would have to have been attached to some sort of leaving group, and you can make up whatever the leaving group is, but you want to pick something that's a pretty good leaving group. So chances are it would probably be like CH3Br or CH3I. Okay, you got a good leaving group here. Now, of course, in this case, it would also be CH3Br or CH3I or some other really good leaving group. Now, which of these two scenarios would be more likely? The terbutoxide and the methyl bromide, or the terbutanol and the methyl bromide? What do you think?
I think maybe the first one.
Why?
Because of the negative charge on the O.
And that would make it what?
A good nucleophile.
It would make it a good nucleophile. Mm-hmm. So why wouldn't the OH work on the bottom? Why wouldn't that be a good?
Because it has to have a pair of electrons to donate. I don't know.
It does have a pair of electrons to donate, but if you look at the substitution versus elimination flow chart, alcohols, as far as nucleophiles go, alcohols tend to be pretty crappy nucleophiles.
Okay.
Yeah. Alcohols are pretty terrible nucleophiles. They will not really, they will not give you enough of a hit to knock out a leaving group. So yeah, this is not going to really work. So the top one is a possibility, and you could stop there. But I do want to actually show you another possibility as well, because this other possibility could happen. And I also want to show it to you because I want to draw your attention to other potential considerations you might want to pay attention to. So let's say, for example, instead, let's say if the oxygen was originally on the methyl group, then the nucleophile could either be CH3O-, so it could be a methoxide, or it could be a CH3OH. It just says choose an alkyl halide and a nucleophile that could react to produce the following compound. Okay, so now if these are our nucleophiles, then our substrate, and actually I should probably add the text there. Substrate. I'm lazy, I don't feel like. Okay, the substrate there. Now I'm going to go ahead and draw. Okay, our substrate would be the tert-butyl bromide. So I have the to Br, or whatever other leaving group you'd want to use. And the substrate, once again, in this case, would pretty much be the same either way. It'd just be your tert-butyl bromide. Sorry, I'm a little sloppy in my writing. Okay, so looking at this, which one of these could give you the compound over here? Or could they both do it? What do you think? Sorry, what'd you say? For some reason, your microphone's not working. I'm sorry. You can also type it if you want. Would both of these work, or would only one of them work? For example, for what about the methoxide? Go ahead.
So there's electrons that it can on the bromine that you can use to substitute on the oxygen.
Well, the bromine's electrons aren't really too relevant here. The key factor here is whether or not the nucleophile can effectively come in and whether or not the leaving group can effectively leave. And also there's another factor here that I don't want to give away, if I can get you guys to think of it. What is methoxide?
Does it have to do with it being bulky?
No, it's not terribly bulky. Methoxide is actually not considered a bulky base. But methoxide is what? It is a. Is it a good nucleophile?
Yeah.
Is it a base?
Conjugate base? Oh, yes, it's a.
Yeah, it's a strong base. So what would happen if you reacted methoxide with tert-butyl bromide? Well, let's find out.
Oxygen.
Substitution versus elimination. Tert-butyl bromide is a tertiary leaving group, and there's a strong base present. That means we'd get elimination. Now, why would we get elimination? Because it's important not just to know what happens, it's important to know why it happens. In this case, we would only get elimination for this top combination. This would be E2. Why would it get elimination rather than substitution? Any ideas? It's basically because, no pun intended, the tert-butyl bromide is sterically hindered. This is a very sterically hindered substrate. So the oxygen here is a strong base. It can either try to come in and force its way in as a nucleophile, or it can rip off one of the hydrogens here. And it turns out it's a lot easier to rip off one of the hydrogens than try and force itself into this sterically hindered space. Now, if the oxygen wanted to come in and act under substitution, it would have to wait for the bromine to leave. But the problem is, a strong base is not going to be patient enough to wait for a leaving group to leave on its own. So a strong base will always kind of kick it out. or it'll always kind of rip off. It'll rip off the hydrogen, the beta hydrogen, before you even get a chance. So in this case, that means this would actually be E2 elimination. It would not be SN. It would not be SN2 or SN1. So that would not be possible. What about the last one? Could those two reactants give you the overall product you see here? What do you think?
That alcohol or the OH is a terrible leaving group. So it would.
Well, it is a terrible leaving group, but remember, in this case, is the OH a leaving group we're looking at, or are we looking at that as a nucleophile?
As a nucleophile.
Yeah. But as a nucleophile, how good is it?
Not good.
Not that good. So it's not going to stick itself in there that good, but bromine's a pretty good leaving group, right?
Yes.
And it's on a tertiary carbon. So could that bromine leave on its own?
Yeah.
And if it left on its own, giving you a tertiary carbocation, would even a not so great nucleophile like an alcohol be able to add?
It wouldn't have to undergo any more rearrangements or any rearrangement.
Yeah, you're right. It could not. And I'm glad you actually brought that up, because when it is an SN1 or E1, when you have a carbocation form, you do always have to look for rearrangement. But you're right. In this case, there would be no rearrangement. But can a poor nucleophile act on a carbocation? Can it attack a carbocation? What do you think? Well, the answer is actually yes. A carbocation is so reactive, so incredibly reactive, that even a poor nucleophile can add to a carbocation. So it turns out that in this particular case, this would also be a viable means. This would also be a viable means to give you this. So you could either have this combination of a nucleophile and a substrate, or you could have the one on the bottom. Now, which one would be a better choice in terms to give you a more efficient reaction? The first or the second?
The first one.
First one?
Yeah, absolutely. And that's because that one, because it has a strong nucleophile and a good leaving group, that's going to happen a lot faster. The bottom reaction will happen, but it's going to be slow and it's going to take a lot more time. Very good, very good. I hope that was helpful. Any questions on that before we move on? Okay. So then let's go ahead and hit 6. It says, which alkene in the following pair is more stable? Circle your choice and explain your answer. So which of these is more stable? First one or the second one? What do you think?
The first one?
Yeah, the first one. This is going to definitely be more stable. Now, why?
There's a shorter carbon chain on that would have less chances of being attacked and broken apart. I don't know how to explain it.
Yeah, I mean, those are actually good thoughts. It's not. That's actually intelligent reasoning on that. It turns out in this case that that's not quite correct, but those are actually. I mean, you're thinking about the right things, but in this case, it depends on how fancy or how advanced your professor wants your thinking to be on this. But basically, it's di-substituted. Alkenes are more stable. Di-substituted alkenes are more stable than monosubstituted. Basically, the more carbon groups you have attached to a double bond, the more stable it's going to be. So all other things being equal, you will always find that, or you'll find that more substituted alkenes are favored. This is monosubstituted versus disubstituted. Now, why is it more stable? Just because it's disubstituted as opposed to monosubstituted? Well, that comes down to this interesting fact that when molecules are double bonded, when atoms are double bonded, that actually increases their effective electronegativity. In other words, they actually pull, because they're sharing those two pairs of electrons, they start trying to pull electrons more closely to itself. You can actually think of this in the context of somebody, like if any of you are familiar with being part of a big family. I mean, I'm one of 7 kids, so this kind of makes sense to me as an analogy. But like, if you're from a big family, you're used to sharing everything, and it makes you really want some stuff, like really want, as you get older, to have some stuff of your own, like not just like always be sharing with somebody else. But that's an imperfect analogy, but it kind of works. But essentially, the more bonds it's sharing, the greater the effective electronegativity, and the more strongly these carbons pull on electrons. Now, if you have carbon attached to the double bonded carbon, then you can get hyperconjugation. You can actually get the sharing of electrons from these adjacent carbons, these allylic carbons, to those carbons that are double bonded. And with 2 carbon groups, you'll have 2 of them that are donating. With 1 carbon group, you'll have 1 of them that's donating. So the more that it donates towards that carbon, the more stabilizing the effect is. In this case, tetrasubstitute, if there's 4 carbon groups, that'd be more stable than tri, which is more stable than di, which is more stable than mono. Does that make sense? I know that's a lot.
Yeah.
Okay, cool. Now this is a fun one too. All right, it says, predict the major and minor elimination products of the following reaction. Okay, it kind of gives it away and tells you that it's the elimination. But if you did not know that this was elimination, like if it did not tell, if it just said predict the major and minor products of this reaction, how could you tell that this would have elimination and not substitution? What's the first thing we look at?
If it's on like a secondary carbon.
Yeah. In this case, what kind of carbon is it on? What kind of carbon is the leaving group on? So we first ask, where's the leaving group?
On the second carbon, so it's disubstituted.
Well, it's not disubstituted in here, and like we don't refer to leaving groups as being disubstituted or anything like that. We would say that they are either primary, secondary, or tertiary. In this case, how many carbons is that leaving group carbon attached to?
3.
3. So this would in fact be what type of leaving group?
That's on the tertiary.
It would be tertiary. So you have a tertiary leaving group, and then you look at the potential nucleophile or base, and is OH, first we ask, is it a strong base? So is OH minus a strong base? What do you think? Is OH minus a strong base?
Yes.
Yeah, so this is a strong base. And is it a good nucleophile?
Yes.
Yeah, it's a good nucleophile. But in this case, because you have a tertiary leaving group, it doesn't matter that it's a good nucleophile. I'm actually not going to care about that. The fact that it's a strong base means it's going to be elimination. Now, elimination always occurs from the beta hydrogens. That's an important point to make. Elimination always occurs from the beta hydrogens. So it's going to be either these hydrogens or the hydrogens on this carbon, or it's going to be the hydrogens on this carbon. Your beta hydrogens, these are going to be the hydrogens that are ripped off. Now, so we actually have to predict all the products. So in the first case, let's say we rip off one of these hydrogens over here. If I rip off one of those hydrogens, it's going to actually cause the electrons to form a double bond here and kick out the iodine, right? Because the double bond's always going to be in between your beta carbon and your leaving group carbon. So we get 1, 2, 3, 4, double bond, 5, and then I have a carbon group up here and a carbon group down here. That's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, good. So I have the right number of carbons in the chain. So this is my one possible product. The other possible product is if I took off one of these or one of these. Now in this case, because these are both one carbon groups coming off of this carbon, it would pretty much give us the same thing either way. 1, 2, 3, 4, 5, 6. So it'd be here. Or you could also put the double bond down here. But in that case, in either case, it would be, and I'll actually just draw it to make it totally clear why it's the same. But essentially, these two are essentially equal to each other because the, there you go. These two are essentially equal to each other because it would still be 2-methyl-1-hexene. 2-methyl-1-hexene. In either case, they would have the same name. It's just you can really, basically, essentially, you can rotate around this bond right here because you can rotate around single bonds. And if you did, that would just split these two positions right here. And you would get the same thing. Does that make sense? You guys are so quiet today. That's okay. Yeah, I definitely encourage you to feel free to talk and actively be involved. But if you don't like the sound of your voice or you don't want to, that's okay too. All right. So which of these then, since you really only have two products, you have this one and this one. Which of these would be the major and which would be the minor?
The major
and
is
why?
the first one. Because it's more substituted.
Therefore, this would be the minor, right? All right, good deal. Now, what about if this, instead of having an OH, you had KOCCH3, 3. What if instead of OH you had this? Which would be the major and which would be the minor? Would it be the same?
No, it would be the bottom one because it's bulkier, so it's going to take one off the end.
Yeah, the steric hindrance, even though the more stable product would be the first one, steric hindrance and the fact that it's a big bulky base would cause the less highly substituted product to be the major product if you had a big bulky base. And she might throw something like that at you. You know it's true. So this would flip major and minor. Sorry, my writing is atrocious on the computer. Okay. So what do we want to do next? Should we just go on to 8, or what do you think?
Yeah, I feel like just keep going. I don't know what
Okay.
everybody else wants.
Keep
All right.
going.
All right, sounds good. It says draw both the E1, two possible products, and the SN1 of the following reaction. Now, in this case, of course, because there is no strong base, right? We have a weak nucleophile, we have a weak base, and a weak nucleophile. And in that case, it's not going to force anything to happen. It's going to have to wait for iodine to leave. So iodine will leave, and that will give you a carbocation. Now, as in any E1 or SN1 reaction, we should always check and see, will there be a rearrangement? What do you think?
No.
No. And the reason that there's not going to be any rearrangement is because you'd have the blue, the beta carbons are all in less favorable positions. A tertiary carbocation is better than either a secondary or a primary, which these other positions would be. That would be like getting a really good deal, buying a TV for like $250, and then taking it back to the store and buying it somewhere else for like $500. So that wouldn't be very smart. And molecules are smart. They're not going to do that. All right. So then what you're going to go ahead and do is you're going to either have water, which has a lone pair of electrons. So it can act as a base, but it would be a weak base. It can act as a nucleophile as well. If it acts as a nucleophile, what's it going to do?
Attack the cation.
Yeah, it'll attack the carbocation. It's going to join right here. And that would give you that would give you this. Well, strictly speaking, it would actually give you this. An OH2 plus, and then you'd have to have another water molecule come and take off that extra hydrogen and turn this into the alcohol, and that would give you OH. So there's our substitution product. That's our only possible substitution product. You can then also get an elimination product, two of them. And the elimination products will be pretty much the same ones that we got before. And for pretty much the same reason, it's going to either abstract one of the hydrogens here or here, or it's going to abstract one of the hydrogens here. And in that case, you'll also get the double bond here. And 1, 2, 3, 4, 5 double bond here. Now, going back to our substitution elimination flowchart, there's not a strong base, there's not a good nucleophile. The question then that actually determines which one of these is going to be the major product is heat added? If you have heat added, the major product would be elimination. If there's no heat added, then substitution would be the major product and elimination would be the minor. I'm not sure if she's going to expect you to know that, but in this case, since there is no heat listed, this would probably be your major, and the other two would be your minor. However, of the minor products, this one would be obtained in greater amount. All right, so let's do the next one. The following reaction does not give the product shown. Explain why this is the case and give the most likely product. What do you think?
You have a strong leaving group with a methoxide. That's a good nucleophile.
It's a good nucleophile.
But it's forming an alkene.
So yeah, it's also a strong base. Well, notice it says the following reaction does not give the product shown. Why is this the case?
Because the methoxide and the bromine do not, they make an SN2 reaction.
It does make an SN2 reaction, so you are correct. So the reason it makes an SN2 reaction and the reason that is preferred is because even though methoxide is a strong base, it is also a what?
Strong nucleophile.
It's also a strong nucleophile. And when the leaving group is on the primary carbon, it's not very sterically hindered, right? So a strong base that's a good nucleophile in the absence of any steric hindrance will always prefer to act like a nucleophile. However, if it's sterically hindered either by a secondary or by a tertiary leaving group position, it will prefer to do elimination. So in this case, yeah, you get the substitution. And good call on that, recognizing the SN2. Well done. All right. So let's jump to number 10. Unless there's any other questions. If you have any questions, please feel free to stop me. I'll go back and explain whatever you have a question about. Now, number 10, it says draw a stepwise mechanism for the following reaction. Okay, so this is an interesting one. So we have our oxygen. What's the first thing that's going to happen here?
A deprotonation.
Yeah, well, not a deprotonation. Well, a deprotonation of something, but
that
yeah.
alcohol is on there.
Now, I think your professor would probably allow you to get away with just drawing this as an H+. But if they were really mean and they wanted you to draw the formula for H2SO4, here it is. All right, so this then, change my color for the mechanism, arrows. Just going to grab the hydrogen here, and that's going to put those on here. And that's going to give you our first and then I have an OH2 rather. OH2 has a positive charge on it. So what's going to happen next? Sulfur. Go ahead.
I was thinking that the hydrogen or hydronium would come in and attach or to remove one of the hydrogens. Oh no, that's backwards.
And not exactly. What's going to happen here is that the leaving group is going to leave because This is H2SO4 and HSO4 minus are both terrible nucleophiles. They're not going to come in and attack this. This is going to have to leave on its own. This is going to have to leave on its own. And when it does, you're going to get a new molecule. Still got this, but now I have a positive charge right here. So now at this point, what should I be looking for? Anytime there's carbocation formation, what should I be looking for?
Nucleophilic attack.
Potential nucleophilic attack, but do we have any good nucleophiles?
No.
No. But even before nucleophilic attack, what should I be looking for?
A methide or hydride shift?
Yeah, a carbocation rearrangement. We need to make sure that we're looking for carbocation rearrangement, because anytime a carbocation can form, you can have carbocation rearrangement. Now, will you have carbocation rearrangement in this case? You look at the carbons next to the, triple, like the carbocation.
Yeah.
What kind of carbon is the bottom one? Primary, secondary, or tertiary?
Secondary.
Secondary. What kind of carbon is the top one?
Tertiary. Well, quaternary.
Quaternary. Yeah, quaternary. Very good. So this is a quaternary. So which will the secondary carbocation switch with? Undergo a shift with either one of these?
Probably the bottom one.
Not the bottom one. That would just be like a secondary to a secondary. That's like taking that TV back to the store and then buying it somewhere else for the same price. Yeah, you could do it, but what's the point?
So would it rearrange to the quaternary one?
Yeah, it would rearrange to the quaternary one. You'd end up getting a methyl shift. It's more highly substituted, but so you end up having to shift not just a hydride, but a whole methyl group here. So you get a methyl shift rather. And then that's going to rearrange this to a molecule that looks like this. Now, the carbocation is now here. Now, just as a point of note, if I was to show all of the bonds to each of these atoms, which I could, I would basically be like, okay, well, you got a hydrogen here, and then hydrogen here, 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 and here. So notice I still actually have a hydrogen here. So when this methyl shift comes over, this carbon now has 4 bonds. It has no carbocation. But this one up here has only 3 bonds. So it is going to have the carbocation. I know that some students kind of get a little confused. Like, well, why is the carbocation up there now? And it's because it now only has 3 bonds, and that's why it has a carbocation. So there's your carbocation. And actually it's important for me to actually draw these hydrogens now because I've shifted the location of the beta hydrogen positions, or rather shift the location of my carbocation, giving me different beta hydrogen positions. So now I have a different group of beta hydrogens. So I can actually either look at this, or this, or this. So these are my 3 beta positions, beta to the carbocation, and I can choose which one I'm going to remove to give me the double bond. Now, strictly speaking, you will get all 3, but one of them will be the major product. And in this case, it wants the reaction that goes from here to this one. And so for this one, it's clear that the hydrogen that's going to get removed is which one?
The bottom right one.
Yeah, the bottom right one, right? This one, right?
Yeah.
And Amanda, you have not talked this entire time. That is unacceptable.
Dude, I'm so in over my head.
All right, so basically, these electrons are going to grab this hydrogen here. That's going to cause these electrons to form the double bond. And that is what will give you this. So notice this is acid catalyzed. Alternatively, one could say that the HSO4 minus grabs this hydrogen, but it doesn't really matter. It's either the HSO4 minus or water. Water is a better base than HSO4 minus, so I'm just saying that. Any questions on this mechanism? Does this make sense?
I mean, yeah, when you do it.
Yeah. It seems like a lot.
Yeah, the acid catalyzed dehydration of alcohols is actually one of the more challenging mechanisms that you're going to have to actually know here. The key point is to recognize that the alcohol is not a good leaving group on its own. So you start by protonating the alcohol. The alcohol is going to leave on its own. It's not going to be kicked off. I mean, typically speak, I guess it could be kicked off. It could be kicked off if it was primary or secondary and you had a good nucleophile. For example, if this was like, instead of elimination, it was HBr. But in this case, it's H2SO4. Anytime H2SO4, it means the leaving group's going to have to leave on its own because it's not going to be able to be kicked off on its own. Okay, so in that case, so protonation of the alcohol, leaving of the leaving group, leaving of the water. Check and see if there's carbocation rearrangement. There oftentimes is, but not always. And then, last but not least, elimination of the beta hydrogen by water, the conjugate base or something like that. And that'll give you the alkene. And I can guarantee you with almost 100% certainty that she's going to throw a question like that on your test. Because that is kind of an important mechanism to know.
That is good to know.
Mm-hmm. Now, a similar mechanism, once again, is 11. Now, once again, if you reference what I mentioned, the substitution versus elimination flowchart here for 11. Actually, let's reference it for here as well. So here you had, is first asked, is there a good leaving group? And the answer is no, but it also says, can you make it a good leaving group? And the answer is yes. You can protonate this to make it a good leaving group. So then the answer is, where is the leaving group? It's on a secondary position. So secondary, here we go. Actually, I'm going to go ahead and erase all this trash. Okay. So yes, it's a secondary leaving group. Is a strong base present? No. Is there a good nucleophile? No. Is heat added? Well, probably. Actually, heat would typically be added with this. But yeah, so this ends up being E1 elimination with that first one. Typically, they would say that heat is added. In this case, there's really no good nucleophile, so concentrated will always give you the base, rather the alkene. But if you look at this one down here, stepwise mechanism predict the product. Okay, is there a good leaving group? No. Can you make it a good leaving group? Yeah, if there's an acid, which there is. OH can be a good leaving group if you add an acid to it, if you turn it into water. And where is that leaving group? Where is that leaving group? What
Primary.
carbon is it attached? Primary. So if we're looking at the primary now, is there a strong base present? Well, no, there's a strong acid present, right? So the answer is no. Is there a good nucleophile? Well, Br is a good nucleophile, isn't it?
Yes, yeah.
So there's no base, but there is a good nucleophile present. So that means we're really looking at an SN2 reaction. And if it's an SN2 reaction, are we going to get carbocations?
No.
No. So what's the first step in this reaction?
Nucleophilic attack?
Can't have a nucleophilic attack if you don't have a good leaving group.
We have to add water to remove the OH.
You have to add an H plus, right?
OH.
You have to protonate the alcohol. So I'm going to go ahead and protonate the alcohol. The alcohol is going to, OH is going to grab this hydrogen. It's going to kick out the electrons onto this bromine. And that's going to give you the first step product, which is, and then OH2. Admit it, you love the theme music.
It does add intrigue.
Oh man, I love you guys. You're so much more fun than the Gen Chem students. Don't tell them I said so. All right. So now what do we do? Is this going to leave on its own, or what's going to happen here?
Hydronium could be added, or
The bromine's gonna attack now?
Bromine is going to attack now. Yeah,
Like-
that's actually what's going to happen. Because water can't leave on its own. Remember, it's a primary carbon, or it's a primary leaving group. And primary leaving groups, they may be good leaving groups, but they can't leave on their own because primary carbocations are ridiculously unstable. So this bromine is going to come in. It's like, take my hydrogen, will you? Boop. Kick that guy out. Now, because it's an SN2 reaction on a primary carbon, is there going to be a stereochemical? Do I have to pay attention to stereochemistry here? Yes or no?
Yeah.
I don't know. No.
Actually, yeah, it's no, because there's going to be no inversion of stereochemistry. I mean, yes, there is a stereochemical center here, which is not going to change from where what it was previously. I mean, this is going to be like 1, 2, 3. So this is actually a S to start with, and it's going to still be an S after the bromine kicks this out. But the bromine is not going to form a stereochemical center because this carbon, the one right here, already has 2 hydrogens. And if it has 2 hydrogens, it can't be a chiral center. It has to have 4 different groups to be a chiral center. So boop, boop. 1, 2, 3, 4, 5. Now the bromine is here. And it's happy. And the hydrogen's here. So this is a relatively simple mechanism. Just involve 2 steps, protonation of the alcohol and then nucleophilic attack to get rid of the leaving group. And you have that and water are your products. Yay! That is not an O. Okay. Make sense? Is chemistry our best friend? Say yes.
A frenemy.
Yes, indeed. All right, but we're good with this? This makes sense?
Yeah.
Okay, cool. Now it looks like we only have one more problem left. It says when cis 1s 2r 1-chloro 2-methyl cyclohexane is treated with or heated with hydroxide, the reaction is fast and the product is 1-methyl cyclohexane. When trans 1r 2r 1-chloro 2-methyl cyclohexane is heated with hydroxide, the reaction is slower and the product is 3r 3-methyl cyclohexane. Write a few sentences explaining why this is the case. So, anybody have any ideas before I go ahead and explain this?
The chlorine is a good leaving or a good nucleophile, and the leaving group. Chlorine is the leaving group.
Chlorine is the leaving group, that is correct.
The OH is the strong acid, strong base,
OH is a strong base.
and the chlorine, the chloro, is on a disubstituted carbon or secondary. So try to remember the flow chart. Is it if it's heated, it's an E2 mechanism?
Well, in this case, the first thing to look at is, okay, the leaving group is secondary, right?
Yeah.
So it's secondary. And then, is there a strong base present? Yes. So I'm just going to erase all my junk. Okay. So it is a secondary leaving group. A strong base is present. The base is a good nucleophile, but it's not sterically hindered, and it's not sterically hindered. The truth is, if the base is a good nucleophile for a secondary carbocation, it doesn't matter what else happens. You're still going to get E2 as your major product. Okay, SN2 is going to be a minor product, even if it's not sterically hindered, as in this case. But since it's E2, what do you know about the elimination, E2 elimination? The hydrogen that's removed has to be, the hydrogen that's eliminated has to be which one?
Beta hydrogen on the substituted carbon.
It will be the most substituted, so you are correct. But then why do we get the less substituted one removed here? Because it's clear we have two beta positions, right? I'll go ahead and highlight them. See, here's your beta carbon here. Here's a beta carbon here. Beta carbon here. Beta carbon here. Now, in this case, it's the, and in the bottom case, we have these guys, one of these guys that gets removed. In the top case, we have this guy that gets removed. Why is that the case? Because it's not sterically hindered in either case. OH minus is not a sterically hindered base. This comes down to what's referred to as anti-paraplanar position or anti-coplanar. Whenever you have elimination occur, if you were to draw a Newman projection, so you have a Newman projection. Let's say if the leaving group is up here and the hydrogen to be extracted has to be down here. So for E2 elimination to occur, the leaving group that has to leave has to be pointing in the opposite direction, has to be anti to the hydrogen on the other carbon, the beta carbon. And this is called anti-coplanar or anti-paraplanar. It's called anti-paraplanar in rings because it's not a perfect, it's I think it's not a perfect coplanar situation, but it's close enough. So antiparaplanar or anticoplanar hydrogen is needed to cause this elimination to occur. If you look at the top one, you'll see that the hydrogen is dashed, right? And the chlorine leaving group is wedged. So in that case, if you were to draw, and you don't have to do this, by the way, like for the purposes of the test, it's enough to you to recognize that they're on opposite sides. The hydrogen's wedged and the chlorine's dashed. I mean, the hydrogen's dashed and the chlorine's wedged. But if you were to draw this as a, let's say, yeah, let's do it like this. A chair conformation, like this. Let's say, oh shoot, I messed that up. I do it like this. That looks terrible. Okay. So all right, well, I'm just gonna run with this. I'm gonna say that, let's say it's in this position, and this is your carbon. The CH3 is up, and the hydrogen is out here. Or in the chlorine is up, and the H is down here. Now in this conformation, it would not work. It would not work. Instead, what happens is you have to actually flip this upwards, and if this carbon flips up to this position, this chlorine is now going up, straight up, and the hydrogen's going down here. But the other one, which I'm actually going to mark in a different color here, just to kind of point out to this is actually now this carbon. And you get the hydrogen is down now, and the methyl group is still up, but it's equatorial. See, now because this chlorine is up and this hydrogen is down, they end up being anticoplanar to one another, or antiparaplanar to one another, and they can be eliminated. However, if you were to look at, so this is both for this top situation. These are both for the top situation. But if you looked at the bottom one, see the hydrogen here is dashed, and the chlorine is also dashed. So they're actually on the same side, and there's no way for them to be on opposite sides. If you were to look at this, you'd see, okay, well, yeah, the CH3 is up here, and the hydrogen's down here, and the chlorine is down here, and the H is here. But notice that the hydrogen and the chlorine aren't pointed in opposite directions. And if you flip them, they would still not be pointing in opposite directions. So for the elimination to occur, the hydrogen that's to be abstracted, the beta hydrogen to be removed, has to be pointing in the opposite direction. So if it's dashed here, the leaving group has to be wedged, or if the hydrogen is wedged, the leaving group has to be dashed. So in this case, because they're in opposite positions, the elimination can occur and you get this product. In the other case, the hydrogen, because it's down relative to the CH3, and the chlorine is also down relative to the hydrogen that's it's with, they're both down relative to the other species, there's no way for them to be anticoplanar or antiparaplanar to each other. And so this cannot act. This cannot be eliminated to form the double bond here. So as a result, you end up having to use whichever one of these is opposite. In this case, the dashed one, it would have to be opposite to that dash chlorine. The wedged hydrogen here would be opposite to the dash chlorine, and that would be the one that gets used, and that's why you get this product. Does that make sense? I know I said a lot. Any questions? If I were to recap this problem in simplest terms, what I would say simply, and this is kind of busy. I'm gonna go ahead and erase a lot of this, okay? Really what it comes down to is one simple thing. Okay. If the dash hydrogen or the hydrogen is in the pointing in the opposite direction as the leaving group, then you can eliminate with E2 elimination and you can get that product. If the hydrogen is facing in the same direction as the leaving group, it will not be able to be anti in a ring and you'll get the other product. So any questions? You guys are too quiet. Tell me you have questions. Speak now or forever hold your peace.
I think it's just overwhelming.
Yeah,
That too.
I get that. I do also want to mention one more thing, and this is kind of evil, and I'm sorry. This is just the nature of the beast. But let's say, for example, you had a benzene ring here, okay? And let's say you had a chlorine leaving group here, okay? And let's say you had an OH or something. If you reacted this with an OH minus, what would the major product be? See, in this case, the hydrogen is on the same side as the chlorine, right? Y'all can see that?
Yeah.
But because this is not a ring where the beta hydrogen and the leaving group are not present in a ring, you can actually rotate this around. So if I rotated this around such that I put chlorine in the back, the methyl group would be in the front. So I rotate this around such that now the chlorine has been shifted to the back position. The methyl group ends up being in the front position. Note that the other group here, the other group attached to that carbon here, is a hydrogen. It's just not shown. That hydrogen is down here now. And you have the CH3 up here. So in a case where it is in a case where you can rotate around the single bond to make them anti to each other, to make them on the opposite side, because remember, it's the here is your leaving group, and here is your beta carbon, your beta carbon position. Now this over here is also a beta carbon, but keep in mind, we're wanting to, this is not a sterically hindered base, so we're wanting to grab the hydrogen that's going to give us a more highly substituted product. And in this case, because there's only one hydrogen on the more highly substituted carbon, we're only going to get one major product, which is going to be a Cis product in this case, or some derivation of that. So it'll be like this. You'll have down, double bond, and then a carbon up here. Because the chlorine and the hydrogen, these are both going to be abstract. That's going to be ripped off. The hydrogen's going to come here, or the electrons are going to come here and kick this chlorine off. And it's going to be locked into this position. It's going to be locked into this shape. You will not get this. You won't get this. That's not possible. Because the hydrogen has to be opposite to the chlorine leaving group. Does that make sense? I just wanted to show you another iteration of that problem because it is very possible you could get either one of those. Either the ring question here, in which case only one beta hydrogen could mean that you don't get a reaction there in that position. Or in this case, in which one beta hydrogen means you still get a reaction in that position because it's not a ring, but it does give you a different stereochemistry than you would get if they were in opposite positions. Now, if there's anything that I've explained that I haven't done a sufficiently good job of, please let me know. I'm happy to try to explain it in another way. Do you have any questions for me over this? Anything else I can clarify?
I don't think so.
I just feel like I need to memorize that flow chart.
And what I would recommend is don't simply memorize the flow chart, because the flow chart, yeah, they'll be helpful, but don't simply memorize the flow chart. I want you to ask yourself the questions and answer the question, why is that the case? So let me give you an example. Let's say I'm doing an example like, okay, where's the leaving group located? Primary, okay. Primary leaving group. Is there a strong base present? Yes. Is the base a good nucleophile? Yes. Is it sterically hindered? Yes. I get E2. Okay. Well, primary primary leaving group, strong base present means it can either do elimination. If it's a good nucleophile, it can do elimination or substitution. Well, strong base means you can get elimination, E. Good nucleophile means you can get substitution. So then the question is, which one is going to be favored? Is it sterically hindered? Yes. So why does it give me elimination only? Because even though it's a good nucleophile, it's sterically hindered. So it can't get to the backside attack. It's just going to rip off a beta hydrogen. Or in the case of strong base present, is a strong base present? Let's say it's no. If the answer is no, is there a good nucleophile? Yes. Well, then you're going to get SN2 only. Well, without a base, elimination can't occur, so only a good nucleophile can give you the reaction. What if there's not a good nucleophile? No. Then there's probably not going to be a reaction unless you add a ton of heat and you have something like H2SO4. And if you add a ton of heat and concentrated H2SO4, yeah, maybe you'll get an elimination reaction. But that's a rare situation. Or if, for example, what if you have a tertiary carbocation? Is there a strong base? Well, let's say there is. Well, why won't you get substitution? Because the tertiary carbon, the leaving group is too sterically hindered to have a base come in, or to have a nucleophile come in if that nucleophile is also a base. You'll end up getting elimination because no nucleophile is going to be able to get in for a backside attack on a tertiary carbon. Now, if there's no strong base and you do have a good nucleophile, the good nucleophile will have to wait for the leaving group to leave, but then it's going to jump in there. It's going to have to wait for the leaving group to leave, but then it's going to jump in there, and you're only going to get SN1. But if you don't have a good, strong base, so there's no elimination. So no elimination. And you don't have, well, at least you wouldn't expect there to be elimination right off the bat. And then there's not a good nucleophile. The nucleophile tells you there'd be substitution. Well, then what's going to happen? Well, if there's not a good base and there's not a good nucleophile, then you have to ask, is heat added? And the reason is because if heat is added, then a weak base will be more easily able to rip off a hydrogen, and that gives elimination as the major product. But if there's no heat added, then the major product will be substitution, because it'll be easier for the weak nucleophile to attach to the carbocation than it will be to rip off a hydrogen. So not just what happens, but why does it happen? And there is another factor here that's also worth considering, and that is the factor of solvent. Polar Protic solvents. And actually, let me go ahead and make a note of that right here, because this is something I do want you to take away from here as well. Polar Protic solvents, such as alcohol and water, basically anything with H bonding, hydrogen bonding, so ammonia would also work here. Polar Protic solvents tend to favor SN1 or E1 reactions. In other words, they stabilize carbocations. However, polar aprotic solvents, and those would be things like ether, ethers, or something like that, or chloroform, CH3Cl, or something like that. Polar aprotic solvents, things that are polar but they don't have hydrogen bonding, they tend to favor SN2 or E2 reactions. Now, it's not an absolute thing, and in most cases, this substitution versus elimination flowchart will be a much better guide for you. But it's sometimes useful to know the polar protic versus polar aprotic, especially when you're talking about secondary carbocations. For primary and tertiary, it's pretty set in stone. Secondary is the one that's flexible. That's the one where you have to be a little bit more concerned. It's a little bit more tricky because you can get everything with the secondary. You can get SN1, SN2, E1, or E2, depending upon what you have. And in fairness, this is probably one of the most difficult units in all of Gen Chem, or in all of OChem 1. Any other questions before we wrap up? You've been with me a while, so I probably don't want to keep you too much longer.
I don't think so. Thank you, though.
You're welcome. I do definitely wish you guys the best. Keep in mind, there is an answer key for this entire test also, although we did actually go through the whole thing, up on the website. I will be actually posting this to YouTube, and I will actually send it out to your class just to, as anyone, for anyone who didn't make it, or if you all want to rewatch any part of it that you think would be helpful. So, yeah, I wish you guys the best, and go knock it out of the park, okay?
Okay, thank you.
You're welcome.
Thank you so much.
You're welcome.
Yep, later.
Bye.